All right, let's talk about something that drives a lot of us a little crazy in math class. The rule that says you absolutely cannot leave a square root on the bottom of a fraction. You know the one. It can feel kind of random, right? But it turns out there are some really solid reasons for it, both from, way back in the day and for where you might be headed in your math journey. So let's dive in and figure this thing out.
I mean, it's a totally fair question, isn't it? You solve the problem, you get the right number, but then you lose points just because of how it's written. It's super frustrating. In this explainer, we're going to pull back the curtain and find out why this rule even exists and why it's actually more than just some quirky math tradition.
Okay, so let's get right to it. This whole process, this thing we have to do, it has a name. It's called rationalizing the denominator. And the original reason for it is, well, it's a pretty cool peek into a world before we had calculators in our pockets. This comment from a Reddit user really hits the nail on the head. Imagine a time before calculators. If you needed to know the square root of 2, you couldn't just type it in. You had to look it up in these huge books of tables. And that table would tell you, hey, it's about 1.414. Now, think about doing long division by hand. 1 divided by 1.41421? Yeah, that sounds awful. And this comparison just makes it so obvious. On the left, you have that nightmare division problem we were just talking about. But look at the right. After we do our little trick, you're just dividing that same decimal by 2. You can practically do that in your head. It's going to be about 0.7. See? The whole logic, back in the day, was about making the actual arithmetic way, way easier for a human to do. So let's just get the official definition down. Rationalizing the denominator is literally just the act of kicking that irrational number, that pesky square root, sometimes called a surd, out of the bottom of the fraction and swapping it for a nice, predictable rational number. Let's start with the most common situation you're going to see. You just have one single square root hanging out in the denominator. The good news is, the fix for this is actually pretty simple. So here's the game plan. It's basically a 3-step process. First, always check if you can simplify your radicals. It just makes life easier. Second, and this is the key move, you're going to multiply both the top and the bottom by whatever that square root is in the denominator. Remember, since you're multiplying by what is essentially the number 1, you're not changing the value of the fraction at all. And then third, you just clean up the final answer, simplify it down.
All right, let's see this in action. We've got 6 over the square root of 45. First step, simplify that root. The square root of 45 is the same as the square root of 9 times the square root of 5, which gives us 3 root 5. Perfect. Next, we multiply the top and bottom by that square root of 5. On top, we get 6 root 5. On the bottom, we have 3 times root 5, which is just 3 times 5, or 15. Finally, we simplify the fraction part. 6 over 15 becomes 2 over 5. And our final, beautiful answer is 2 root 5 over 5. The denominator is rational, job done.
Okay, that wasn't so bad, right? That's the simple case. But what happens when the denominator is a little more complicated? What if it's got 2 parts, like a whole number plus a radical? Well, for that, we're going to need a new tool, a little power-up. This is the key problem. You might think, well, let's just multiply by the square root of 2 again. But if you do that, you have to distribute it to both parts on the bottom. You'd end up with 3 times root 2 plus 2. See, you didn't get rid of the radical, you just moved it over. You're just spinning your wheels in the mud at that point.
So, to solve this little puzzle, we bring in something called the conjugate. Now, it sounds fancy, but it's a really simple and powerful idea. The conjugate is just the expression's twin, but with the middle sign flipped. So for 3 plus the square root of 2, the conjugate is 3 minus the square root of 2. That's it.
Now here's the magic behind why this works. It's the difference of squares formula, one of the best tricks in algebra. This is our secret weapon. When you multiply a binomial by its conjugate, the messy middle terms always cancel each other out. You're just left with the first thing squared minus the second thing squared. And what happens when you square square root? Poof, it's gone. The radical vanishes. So our process is basically the same. We're just using a more powerful wrench this time. You find the conjugate, you multiply the top and bottom by it, you let that difference of squares magic do its thing on the bottom, and then you just simplify everything that's left over. Let's walk through one more. We've got 4 divided by the quantity square root of 11 minus the square root of 7. Okay, step 1, the conjugate is just the square root of 11 plus the square root of 7. Easy. Now we multiply the top and bottom by that. On the bottom, we get the square root of 11 squared minus the square root of 7 squared, which is just 11 minus 7. And that equals 4. So now we've got 4 times our conjugate on top and 4 on the bottom. The 4's cancel out perfectly, and we're left with this incredibly clean answer, the square root of 11 plus the square root of 7. So, we've seen the history and we know how to do it. But we all have calculators now. So why is this skill still taught? Why does it still matter? Well, it turns out this isn't just some random algebra trick. It's actually a foundational skill you're going to need for much more advanced math. You know, this same core idea, multiplying by a special something to get rid of a problem, is absolutely essential when you start working with complex and imaginary numbers. The complex conjugate is how you divide them. The same logic also works for cube roots, fourth roots, and beyond. And if you're ever heading into calculus, you will definitely be using this exact technique to solve certain kinds of limits. So what you're really learning here is a fundamental pattern, a problem-solving move that shows up again and again. And beyond all of that, at the end of the day, it's about having a standard, a convention. By having a rule that says the simplified form has a rational denominator, it just makes sure that everyone arrives at the exact same final answer. It creates a standard, a single way of writing the solution that makes it much easier for everyone to compare their work and know when a problem is truly finished. It just brings a lot of clarity to the language of math. So, what's the big takeaway here? We started with a rule that kind of feels like a relic from a world without calculators, but what we found is that it's also a powerful tool for clarity and a building block for some really cool higher-level concepts. So is it a relic or is it a timeless rule? The answer is, it's a bit of both. It's a historical artifact that still provides a ton of value for keeping our mathematics clear and consistent. Thanks for joining me for this one.